All right, everyone. Welcome. Thanks for being here. So for those of you online, Matt was nearly off the hook because we all just had the fire drill here in physical space, but we have happily returned. So it's my pleasure to introduce Matt Long as today's CGD seminar speaker. I also want to thank Matt for being one of our invited presenters at this year's Crocodile and Regional Mom6 workshop. Matt is the CEO and co-founder of Seaworthy. He received a bachelor's and master's in civil and environmental engineering from Tufts and a PhD in oceanography from Stanford. And today he'll be talking about Seaworthy and navigating to solutions for ocean-based carbon dioxide removal. Thanks, Matt.
Thanks, Dan. Okay, so it really is such a pleasure to be back up on the Mesa Lab and see so many familiar faces. It's really been too long, and I feel life just sort of took hold of me and swept me off into this new space. But it's great to reconnect with all these folks, and being saved by the bell gave me the opportunity to have a few nice chats. So I really appreciate actually the fire alarm, whoever was responsible for that. I'll stay around after the seminar too a bit, and maybe it can continue. So I want to talk today about this initiative that I've been working on for the past about 2.5 years. It's called Seaworthy. It's a nonprofit research organization. And what we are trying to do is basically introduce an inflection point in the society's capacity to deploy and manage ocean-based carbon dioxide removal. We're a nonprofit, but we are oriented towards building technological products that people can use in the commercial space. We're also cognizant of the fact that the science underpinning ocean-based carbon dioxide removal remains unresolved. And so there's a requirement to do something that this community here in CGD is very familiar with doing, building a community-based research and development, building a community that can support the research and development initiatives in an interdisciplinary space where the science challenges are diverse, the processes span 15 orders of magnitude in scale, and there's really a requirement to bring together communities of people to probe the solutions, evaluate the tools, and ensure that they track cutting-edge science moving forward. And then finally, we're engaged in capacity building initiatives, putting our tools in the hands of commercial users and research users, particularly in the Global South, so as to build a space for a workforce and an industry that can push carbon dioxide removal forward. I'm really proud of this technical team we've built. We have 14 people on staff. Several of them are in the audience today, and I just want to acknowledge my co-founder and partner in this, Alicia Karspek, who was also an NCAR employee for a number of years. Before getting started, I want to acknowledge our funders. So we're mostly philanthropically funded, and I've included the logos of the philanthropic organizations that have supported us on the top. We also have some, and still have, some federal money from the Department of Energy and NOAA, and then access through DOE and NSF portals for computing. And then finally, we have cultivated a growing and diverse list of partner organizations with whom we are collaborating. Some of these are nonprofit entities in the research space, and others are actually commercial companies, some of which are seeking to deploy ocean-based carbon dioxide removal solutions. Others are registries seeking to establish evidentiary basis and protocols and standards so as to ensure high integrity carbon markets. Okay, getting started. So I don't really need to tell this audience, but the world is warming. Here's a global mean temperature compilation from the Berkeley Earth Group. You can see that recent years have warmed significantly. 2003, 2004 stand out. We've crossed the 1.5 degree threshold, inclusive of uncertainty, as of 2004, though other compilations show slightly different numbers. Most of that warming disagreement is predicated on differences in the estimates of the 1850, not so much the 20th century warming. There's some indications that, well, first of all, warming is very directly related to the greenhouse gas forcing, mostly CO2 that's been emitted into the atmosphere, though there's a decoupling in recent years perhaps related to reductions in aerosol pollution driving an acceleration of warming. We're all increasingly familiar with pictures like this. This is from earlier this year, the LA wildfires, where at the urban-land interface, there is vulnerable populations. NOAA was, until earlier this year, compiling annual statistics on natural disasters in this country in the category of billion-dollar disasters. And this shows a picture of the disasters, the billion-dollar weather-related disasters that occurred in 2024. Here's an example of one of those, the tropical storm Helene, with a study that is aiming to provide some attribution of the excess rainfall attributable to excess warming. The data, when you look at them temporally, looks something like this. This is the count of natural disasters along with the cost in billions of dollars. Notably, we lose something like $140 billion of a year to weather-related natural disasters. Just a fun fact in that space, we earn, as a country, about $220 of GDP related to fossil fuel extraction. So we're losing about 60 cents on the dollar of that investment in fossil fuel. If you normalize the data by population, we see that indeed the cost of natural disasters continues to increase. It's not just an increase in vulnerability, but an absolute cost. And this is showing up in people's pocketbooks. So this is a plot showing homeowner insurance non-renewal rates. There's some market perversions in here, but suffice it to say that there's other problems that we need to worry about. There's tipping points in the climate system, and we don't have very clear understanding for when these might be triggered. Some of them would yield catastrophic results. And we're also driving profound changes in Earth's ecosystem. This is a figure from my colleague Curtis Deutsch, who shows basically on the basis of metabolic theory that we are replicating the end Permian extinction event, which occurred 252 million years ago, driving the extinction of 90% of marine fauna. By 2300, we have, you can see that if we continue with unmitigated warming, there's massive extirpation and significant extinction. And so this presents a very strong incentive to do something about the problem, just on the basis of preserving global ecosystems. So in the midst of all this climate, really an ongoing climate disaster, we're also experiencing massive social upheaval. There's a rise in authoritarian governments around the world and an assault, really, on the fundamental institutions that we rely on as society to make collective decisions about how we invest in supporting large-scale initiatives like those that will be required to confront climate change. In 2015, the United Nations established the 17 Sustainable Development Goals. These are sort of OKRs, objectives and key results for the planet, right? And they relate to human development initiatives as well as climate. Unfortunately, we are not making progress in this space. Only about 18% of the goals are showing positive signs of being on track, and nearly 20% are in regression. Simultaneously, we have a financial system that is overly leveraged, a disruptive AI technology changing the nature of the economy and the distribution of value. And suffice it to say, we live in really interesting times. Maybe we are on one path, through the multiverse, but that path dependency really matters, actually, as we confront what comes next for society on this planet. Okay, are there signs of hope? Well, we have not managed to bend the curve on global emissions. And most of that is attributable to increasing emissions from Asia. Notably, emissions in North America and Europe have sort of flatlined with some marginal decreases. But there are indications that whilst GDP continues to increase, the energy intensity and CO2 intensity of our economies is declining. And that's attributable to large-scale growth in renewables. These comprise still a small fraction of the total energy production globally, but are growing massively. And if you've been watching the news and thinking about what's going on in China, there are incredible trends in technological deployment in China. Here's some projections that show basically the top light blue bars, the renewable energy capacity growth over the past 7 years or so, and then the projections over roughly the next decade. And just the amount of investment and growth in renewable energy in China is really pretty exciting. But in order to meet the targets related to that have been established in international agreements for warming, our emissions trajectories need to look like this, and we are not achieving anything near that level of reduction. Okay, I know, it sounds like a broken record, right? And indeed, the UN Environment Program has characterized it as such. Here are the titles, or the cover pages from the last 4 UNEP reports on the emission gap, getting increasingly cheeky towards the end. No more hot air, please. And so, you know, this is nothing that I've presented thus far is new information. But let's take a look at some of the details of the climate math and think about where carbon removal fits in. So first of all, this plot shows the transient sensitivity to cumulative emissions based on models and to an extent observations. An observation of the climate system is that global mean temperature change is linearly proportional to cumulative emissions since in pre-industrial times. And so what that implies, if it's right, is that if we want to keep warming within a certain prescribed temperature threshold, we need to cap cumulative emissions. It's kind of remarkable that this relationship exists if you think about the climate system and you know, the carbon feedbacks, the climate carbon feedbacks, and all the sensitivities that arise. But suffice it to say, this is a framework that seems to be resilient. And it implies that we have a finite budget, and so the additional emissions that we can emit from this point forward are delineated by these orange bars, having already emitted about 2,700 gigatons. So because we are not mitigating emissions fast enough, we're faced with the prospect of requiring active removal of CDR. I'm switching units on you here. This plot is in petagrams. Petagram C, not CO2, but what you can see is that the decarbonization coupled with net carbon removal is what's required to meet net zero targets and stabilize the climate system. The amount of carbon dioxide removal necessary is potentially quite large. This is a plot showing sort of the ensemble of scenarios consistent with the 2-degree warming target, illustrating that, you know, by about mid-century, there is a requirement to remove from the atmosphere nearly 10 petagrams of CO2 per year. Just for reference, the current global ocean sink for CO2 is 10 petagrams of CO2 per year. And so essentially by mid-century, we're faced with the prospect of having to double the ocean sink, and then out to the end of the 21st century, something like tripling that sink. And if you look at the growth rate required to achieve that, you know, we can't do this instantaneously, and so the requirement to ramp up carbon removal activities is quite profound. The pace of deployment required is quite profound. This has led to a lot of interest in deploying carbon dioxide removal solutions in the ocean. The ocean is already, as I said just a minute ago, absorbing about a quarter. Humanity emits about 40 gigatons of CO2 per year. The ocean takes up about 10, so about a quarter of those emissions, and stores roughly 40,000 petagrams of carbon. It's the largest active sink of carbon in the Earth system. And then it comprises 72% of the planet's surface area, leading to the possibility of deploying carbon removal solutions in absence of conflicts for competing land use. There are several proposed pathways for ocean-based carbon dioxide removal. Those are illustrated here, and they broadly sort of divide into technologies that rely on manipulation of ocean biota, so biotic approaches, and those that are sort of nominally abiotic and involve manipulations of geochemistry directly. So one of the, on the biotic side, we have sort of blue carbon, which is activities that have been going on for a long time, actually, mangrove restoration, seagrass meadows. active seaweed aquaculture and deliberate sinking of biomass. Ocean iron fertilization is experiencing a resurgence of interest and activity, but that entails spreading iron in regions of the ocean that are limited by the micronutrient iron, stimulating phytoplankton blooms that would subsequently sink and remove carbon to depth. And then the two abiotic technologies illustrated here, ocean alkalinity enhancement. Alkalinity is an emergent chemical property, but it describes the buffer capacity of seawater. And so by adding alkalinity to the ocean, we can enhance its capacity to absorb CO2 from the atmosphere. This is analogous to mechanisms that Earth uses on millennial timescales to sort of regulate CO2 in the atmosphere through the weathering of rocks. And then finally, direct ocean removal or direct ocean capture. This is analogous to direct air capture, or DAC, where rather than stripping CO2 out of the atmosphere directly, there's a reliance, or there's technologies to pull CO2 directly out of the surface ocean and then rely on air-sea gas exchange to replenish that CO2 deficit to remove it from the atmosphere. Okay, so how will these technologies potentially be implemented? Well, one of the mechanisms that we're tracking quite closely at Seaworthy is carbon markets. We can build a case that there is value in removing CO2 from the atmosphere. One of the frameworks for doing so is known as the social cost of carbon, and this entails building sort of a scaffolding of coupled model solutions where a socioeconomic model is coupled to a geophysical model that's coupled to a damages model, and so we can sort of track how carbon entering the atmosphere changes the climate with impacts on societies and people, and then in some sense then extract a value estimate of those processes with the glaring requirement to impose a discount factor. And this is one of the reasons why the social cost of carbon is a fraught term in the space, because your assumptions for that discount factor really determine what the solution is. But suffice it to say that reasonable academic studies come up with numbers that are on the order of $150 and $200 a ton, right? So this is a credible estimate of what the value of removing a ton of CO2 from the atmosphere confers, inclusive of the temporal constraints, the assumptions imposed by that discount factor. There are three carbon market mechanisms at play now. So the first is the voluntary carbon market, and that's predominantly the activity that's occurring in this country, where corporate actors have made commitments to their shareholder net zero commitments and are investing in carbon dioxide removal. The EU has a compliance market, and that functions on the basis of regulatory requirements for carbon removal. And then finally, Article 6 of the Paris Agreement provides a mechanism for countries to trade carbon dioxide removal as a component of their nationally determined contributions. There are projections that carbon markets will grow. Those projections are obviously highly uncertain, but now, there's this expectation of something on the order of 5 to 50x growth over roughly the next 5 to 10 years. Recent trends, however, have not been particularly encouraging. There's essentially been a massive contraction of order 60% over the past several years in the voluntary carbon market. And a lot of that is owing to articles like this one on the left in The Guardian, showing that 90% of rainforest offsets are basically specious, or in the New Yorker reporting on very similar manipulations. The problems that have existed in these legacy markets are starting to be confronted, and new sort of focus on mechanisms for ensuring durable carbon removal are emerging in the community. One of the key drivers of these trends is something known as Frontier. Frontier is an advanced market commitment. It is a greater than $1 billion fund to buy carbon removal in bespoke transactions. And this is a mechanism that's been used in global public health to incentivize vaccine development. For vaccines that don't have strong market, an advanced market commitment provides a known market to incentivize R&D. And so Frontier is basically building demand, sending demand signals out into the market. And just recently, for example, cleared a $30 million deal with a company known as Planetary to order 100,000 tons of carbon removal from an ocean alkalinity deployment in Halifax, Canada. So Frontier is a major mover in this space. There are, of course, others. Microsoft has made net zero commitments, committing to remove from the atmosphere, to go carbon negative by 2030, and then remove the cumulative emissions since the inception of the company since 2050. The introduction of AI and the growth of data centers is really complicating Microsoft's position in this space right now. And so it'll be really interesting to see how that evolves. Just to give you a sense of what's going on in the commercial space, this graph shows a collection of ocean-based CDR companies that exist, oriented in columns by the technology that they're seeking to deploy, and then by the rows in terms of their level of maturity. And what you can see is that there is, in the sort of coastal blue carbon and macroalgae cultivation space, a number of companies that have sort of emerged to commercial scale, whilst many of those in the direct ocean removal or ocean alkalinity space have moved through the lab stage and are just beginning pilot and demonstrations. And I think this distinction between the biotic and abiotic mechanisms for carbon removal is really important. We have a lot of faith in the durability of the abiotic technologies, and still have work to do on the biotic side to determine the level of durability of those technologies. But there's a lot of enthusiasm for those approaches. So the carbon market provides a mechanism to inject capital and basically build the technology necessary to deploy carbon dioxide removal at scale. But we can't operate this market unless we can actually quantify the amount of carbon dioxide, the efficacy of these solutions. So that brings us to what's known as open system MRV, or monitoring, reporting, and verification. If we're running a direct ocean removal facility, it's kind of like a factory. It's got fans and pipes and flow meters and gauges, and we can write down kind of an engineering diagram and instrument every flow and every process in this industrial space. And so the challenge of quantification in a DAC plant is actually relatively straightforward engineering, industrial engineering process. The ocean is not like that. Okay, CDR in the ocean works in this two-stage process. The first step is that there's some intervention. Maybe we add alkalinity to the surface ocean. That leads to a depression in the surface ocean PCO2, but we have not yet achieved carbon dioxide removal. What happens next is that air-sea gas exchange replenishes that deficit. And so the challenge associated with quantification entails determining the amount of re-equilibration, or the degree to which that re-equilibration has happened. This presents some significant challenges. The first challenge is that air-sea gas exchange re-equilibration occurs over very large temporal scales. I'm showing you some simulations that we did with the community or system model ocean component, and just illustrating the distribution of the PCO2, surface ocean PCO2 anomaly induced by an ocean alkalinity enhancement deployed off California. So after 1 year, the signal is confined adjacent to the coast, but it spreads such that most of the carbon, such that the reaction, even after 10 years, is still occurring at very basically levels of signal that are indistinguishable from natural variability and spread basically over the whole basin. That leads to the second point. This unfavorable signal-to-noise ratio, right? The ocean is a highly dynamic space with large fluxes into the ocean and large fluxes out of CO2 out of the ocean. And discerning the signal associated with CDR from observations alone is essentially impossible. And then finally, a challenge is related to baseline counterfactuals. So what we need to do to quantify ocean-based CDR is quantify not just what did happen, but what would have happened in the absence of an intervention, so as to compute what's known as additionality or the net removal. So collectively, these challenges imply that ocean-based MRV, or quantification, will have to rely on some combination of observations, but also numerical models. Numerical models will be fundamental to enabling that. And that's just what I'm showing here, that this collection of Earth system science tools and the Earth system science research community really needs to bring all the tools that we have to bear on this problem. Just a final note on the carbon market space, there's some interesting thinking that we can do about the requirements for robust quantification depending on how the market is structured. Right now, the market is structured as sort of a set of, particularly in the voluntary market, bespoke transactions on a project level. And so there's a requirement to have a ton-based accounting framework where the MRV, the quantification, is really precision accounting, attributing carbon removal to the influence of a particular project. But we might imagine that we go to a pay-for-practice model. Let's say we've, a decade from now, we've determined that adding alkalinity to the ocean works. It's a good idea. We know how to do it safely, effectively. And so we can move to something like a pay-for-practice model where really we just fold the carbon dioxide removal activities into the activities that we're already conducting in some sense to track the global carbon cycle. And it's just another term in our attribution budget. And those two, how that market works and how it's structured has a pretty significant impact for the requirements of the science underpinning MRV. Suffice it to say, right now we're definitely stuck on the left-hand side here, doing attribution at the project level, and that's where Seaworthy is focusing. But over time, I think we could anticipate moving more to this pay-for-practice model. Okay, I'd like to just talk a little bit about the initiatives, specific initiatives that we're pursuing at Seaworthy. So first, we are building a standardized modeling system focused on regional scales. Our objectives here are to provide a modeling system that is state of the science and ensures ease of use, transparency, okay, so that it's open source, reproducibility and auditability, so that the end-to-end workflow underpinning a carbon removal credit has visibility and can reproduce a reproducible calculation and provides access points so that a verifier can come in and determine that that calculation was how that calculation was performed and ensure that it was performed according to established protocols. So how this works is we might run a model simulation, simulate the effect of an intervention, compute the net carbon removal from that intervention, and that system sort of condensed to its constituent parts is we have a computational kernel. This is a GCM coupled to an ocean biogeochemistry code. We're using ROMs and Marble. And then an orchestration layer this is the software framework that enables the system to sort of provide simulations out of the box, much like a comp set for this ESM community and a connectivity platform to the computing platform, enabling users to seamlessly deploy the system on HPC resources. And then finally, this integrity layer, which provides the frameworks for codifying the metadata and the auditability touch points, the milestones along that calculation that enable that system to be audited. In more detail, the elements of the CSTAR system look like this. So the system will take in MCDR, CDR, ocean-based CDR activity data. It will do some computation and produce the outputs necessary to engage with the carbon removal market. That is underpinned by, at the center, this ROM's Marble code base. This is an oceanographic model, a GCM coupled to an ocean biogeochemistry code. And then a public catalog where we are maintaining scientifically validated configurations of the model. So out of the box, you can get a scientifically validated regional ocean model configuration, and then work plans that establish these end-to-end calculation sequences necessary to do particular calculations. We're also building community utilities. A key utility in that space is ROMs tools. This is enabling rapid instantiation of new regional domains. So a user can go into the ROMs tools repository and basically have an end-to-end workflow that establishes a new domain, and then begin the process of scientifically validating that domain. Just to point to the documentation here, and some of the, this is the C-STAR documentation. It's up on the web, you can check it out. And then here are some of the links to our repositories. Okay, that was C-STAR. The second thing we're doing is building or publishing community data sets to support the whole variety of use cases related to ocean-based CDR. So these are things like metrics that inform deployment design, where is efficiency maximized, underpin techno-economic analyses so that, you know, as we think about synoptics, the societal level concerns related to scaling ocean-based CDR, there's data underpinning the response of the geophysical system to interventions. And then ultimately, we think these types of data might provide kind of a low-cost framework for MRV. Here's just an animation of one of the data sets that we've published in partnership with Carbon Plan. So this is up on the web at the URL that's available at that QR code. This quantifies the global distribution of the efficiency of ocean alkalinity enhancement and provides a user interface that enables users to sort of drill down and explore signals. So for example, we can look at where the alkalinity of a particular deployment, in this case off the coast of East Africa, goes, or what is the pH anomaly generated by that deployment in a particular downstream region. This is just a very a timeline to just illustrate that what we've done thus far is publish these two global data sets, one for ocean alkalinity enhancement, another for direct ocean removal or direct ocean capture. And sort of our next step in this space is to drill down in terms of resolution and start working at finer resolutions under the premise that global scale models can't capture high fidelity flow. But when we move down to regional scales, we can build much higher fidelity representations of these systems. Okay, finally, the C-STAR Ocean Network. So in this space, this is sort of we have sort of a dual purpose here. One is to build a growing constellation of scientifically validated regional domains, and then actually use that constellation as a vehicle to entrain research partners. And this is something that Alicia and I learned working at NCAR, which is that infrastructure really matters. Modeling infrastructure provides a conduit for bringing together communities of people to collaborate on highly technical research topics. And so the quote here is, technical communities of practice develop organically around effective, low-friction, open-source tools. These form a center of gravity for collaborative development, platforms for synthesis of new research, and a forum to establish and codify consensus on best practices. So what we're trying to do with the C-STAR Ocean Network is actually build kind of a framework for international connectivity around the dynamics associated with modeling for ocean CDR. Right now, the network is comprised of just a few domains. We have one under development still for the Pacific Ocean. This is a 12, and the Atlantic. These are nominally mesoscale resolving solutions at 12.5 kilometers. We have a nested regional system for the Salish Sea and for Iceland. Moving forward, we anticipate deploying model solutions for the Indian Ocean and the Persian Gulf, Arabian Sea region, driven by interest with potential partners in East Africa, and the interest of this ocean-based CDR companies in pursuing deployments in the Middle East, where there's favorable economic and infrastructure requirements. And then over time, we plan to continue building out this system. Just recently, we've started to explore collaborations in Africa, and this is one of the most exciting things I think I've done in a really long time. Just for reference, Africa as a continent has contributed less than 10% of the cumulative emissions burden, but is subject to pretty significant impacts related to climate change. Notably, Africa has the lowest per capita CO2 emission. And so the developing economies of Africa are really interesting because they have this capacity to leapfrog technology. I was a Peace Corps volunteer in Tanzania in the early 2000s, and went back recently to find the system, the visible sort of vibe on the street being predominantly unchanged, and yet the sort of undercurrent of awareness and technology completely changed, right? So the degree of consciousness of the outside world has really undergone a revolution. The thing that I'm really curious about is the degree to which ocean-based CDR, or CDR in general, can provide an avenue to economic development and support for livelihoods. And this is one of the things that we heard quite clearly from Africans, was that the continent has basically decided to focus on adaptation, not mitigation. And so initial reactions to CDR involve sort of a pushback, which is to say, that's mitigation. Carbon dioxide removal is mitigation. We're not interested in that. We're doing adaptation. And following that up with what if CDR came with the potential to improve livelihoods, provide venues for economic development? Oh, well, now we're interested. And so there's a really interesting challenge then in that space, which is to start thinking about how to build the necessary social infrastructure to provide sort of sustainable deployment models for CDR. I actually just got back from Africa on Tuesday after first spending a week in Kenya and running a workshop in partnership with the WIOMSA organization, the Western Indian Ocean Marine Science meeting, and convened a group of about 60 African scientists and politicians to talk about ocean-based CDR. And I can't remember an instance of a more excited, sort of engaged, just active group of people in a professional meeting. At the end of the workshop, we had a banquet, and this guy, Francis Ascuo, on the far left here, stood up at the banquet, and he started to make a toast. And he said, "When I say MCDR, you say one family. MCDR. One family. Well, MCDR. One family." Okay, he went through this call and response and gave just this beautiful, eloquent speech about how these opportunities to engage in research and just sort of confront development challenges as well as knowledge challenges just are really profoundly inspiring. So the vibe with this group was just really incredible. Okay, in the last part of the talk, I'm almost done, but I just want to provide a few reflections on how this is all going to come together, maybe, and what we might think about sort of collectively as a group in terms of the paradigms of science under which we've been operating and how those might need to change in the context of the current social milieu that we find ourselves in, and the really profound challenges of confronting the climate crisis. So I've posed the title of this section as "Who Owns Science?" because I think ownership of science is a really profound and important thing. I was struck by this, in April when Doge was rampaging around the federal government, and thinking about really just the lack of a public response to what was going on. The National Weather Service was being hammered, and the citizenry is sort of like, well, what's the problem? Like, I've got the weather forecast in my pocket, like not really cognating the degree to which large-scale federal investment is a requirement to have functional weather forecasts and functional climate services. And to me, that speaks, of course, taxpayers in this country do indeed own that science, but we've somehow arrived at a point where the linkages in people's minds are broken, and we do not have clear feedback cycles in place. And so I think it's a really curious proposition to think about how, as a community, we can work to change that and build. Perhaps we need new institutions in order to break the molds that have basically been broken in part already. But how do we rebuild, I guess, is the question. So, to start this kind of conversation, I just put up this plot. This shows the shared socioeconomic pathways along with our actual emissions trajectory in this space. And just a moment of reflection, this is kind of the CMIP model, right? There's a group of people who sort of identify kind of internally consistent social scenarios and then throw those over the fence to the geophysical modelers who create climate projections, and then all that information is kind of thrown over the fence to a group of scientists and policymakers who kind of wrestle with the data and make characterizations and sort of recommendations about action. There's a lot to be said for this model, and I think CMIP and associated activities have been hugely impactful on characterizing the problem and positioning us well to understand dynamics in the climate system and advance science. But I think one of the things this model lacks is a clear ownership paradigm in the context of a through line from somebody asking a question upon which asking a question because they need to make a decision about something, and a clear connection to the science that underpins that decision. I think in the context of climate interventions, we need something more along the lines that start with kind of ownership models, and how this looks may differ in different social contexts and different communities. I think it's applicable to research paradigms in this country as well as in the global South. But perhaps there's a space in which we can actually convene communities to determine their long-term interest in pulling climate intervention projects, carbon removal projects to the local community through a process of establishing what viable technologies exist, whether they might project positively on livelihoods, whether they're likely to be safe for local ecosystems, and then really move towards establishing pilots in the water. We're not going to build a scaled ocean carbon dioxide removal industry unless we start putting small amounts of alkalinity in the water and figuring out what happens. And so the whole system sort of pivots on our ability to do field trials. And I think it's been pretty clear from activity in the community of late that actually social license, public skepticism of climate interventions is a key rate limiting step. And so this idea is to sort of flip the script a bit. And then ultimately, kind of use those pilots as opportunities to leverage learning, accelerate the capacity building and tool development that needs to happen, and feed back into that system. One of the key challenges in this space is that the science remains uncertain, and there's sort of a moral question is, can we move forward to sell carbon dioxide removal in a marketplace without full 100% certainty on the science? And my assertion is that we can't wait to finalize the science. We've been on about questions, fundamental questions in ocean physics, ocean biology for decades. And we're not going to basically resolve that uncertainty until it's too late to begin. And so what is really required is sort of a living framework where we engage communities around sort of identifying sort of consensus standards. What is the best available science now? And use those frameworks to operate in the context of early commercial pilots or research deployments, leverage those pilots to then gain learning and to re-inform the best available science, all the while driving or benefiting from the capital injection by selling carbon removal on the carbon market. I think it's pretty clear, just as sort of a macro scale picture now, is that the requirements for investment in a vibrant global scale Earth system science community is really critical. And if we just sort of look at the components of what a verification ocean MRV platform looks like, the sort of core layers, the data, observations, and computational layers are big problems. They're large-scale observing networks, they're community codes, and these things require large-scale investment. It's actually very difficult to conceive of a world where a privatized model works in that space because the value of an incremental investment has is a diffuse value proposition. If you buy one Argo float, $100,000 investment, the data from that float provide very little value in isolation. But once we have 3,000 of these things, then all of a sudden we're off to the races and have a very robust system. And so these sort of top layer things really are collective obligations. A worrisome prospect, as the federal government in this country has indicated it to be at least untrustworthy partner in that space, and regaining, maybe there's an opportunity to regain trust, but I think understanding what are the paradigms for collective investment for these large-scale requirements is really important. But then there are also a lot of opportunities for private entities to move the needle and deliver value in the context of this space. And those public-private partnerships, I think, are something that we really need to redefine as a community and get better at to be more nimble and more responsive to the questions that decision makers have. Okay, just a final note, which is to say that the climate math tells us that we are blowing past targets, and that over the next few decades, it's likely that we will not have achieved the carbon removal necessary or the mitigation, CO2 emission mitigation necessary to stabilize the climate system. And there will be undoubtedly interest in deploying solar radiation management. And so I think there's a degree of urgency in not just figuring out how to do the machinery and social dynamics related to managing carbon dioxide removal as a climate intervention, but also using that as a use case to understand how to manage climate interventions more generally. Because as time progresses, the possibility that we'll be faced with very difficult decisions is a near certainty. And so as all these challenges that we're facing in terms of the ability for effective governance, effective investment models, effective deployment models for science are really important to work out so that we are well poised to address this fundamental problem. Okay, with that, I will turn it over to questions. Thanks.
Awesome, thank you so much, Matt. We have time for questions, and I do plan on going maybe 3 or 4 minutes past the top of the hour because we got started late. So if you are online, you can go to slido.com, and it's hashtag CGD seminar, and so we can have questions from online. And then Paul, just confirming, are the ceiling mics on? Excellent, thank you. So we can start with some questions from the room. Derek.
Yeah, so Matt, I wonder if you say a little bit about the technology that's involved with the alkalinity method. How does it work and how you deploy it?
Yeah, so there's 2 basic ocean alkalinity enhancement approaches. One is called mineral ocean alkalinity enhancement, and the other is electrochemical. So in the mineral phase, it's basically crushing up rocks, putting them in the ocean, waiting for them to dissolve to the greatest degree of simplicity. The electrochemical approach involves building electrodialysis cells that have membranes. Those membranes are either high voltage potential and actually split seawater or brines into an acid and base stream, release the base stream back to the ocean. That leads to the alkalization, and then neutralize the acid stream in some other way, perhaps using mine waste or on land.
Sean, did you have a question?
Yes, so really great talk. I'm curious, so I've seen a lot of recent papers doing more direct attribution of like GDP and like economic damages to specific emitters, like what Justin Makin's done. Do you see litigation and like sort of that legal space of CO2 emissions folding into sort of what you do in a way potentially the federal or international court sort of being involved and integrated into CDR saying, oh, okay, well, if you're emitting this much, then you're forced to contribute this much to these markets?
Yeah, that's, I think, a super interesting, fascinating question. The short answer is I don't know.
Sure.
But I think from the perspective of Seaworthy, I have a very clear answer, which is no. We do not engage in that space. Our goal is to equip the commercial sector and to some extent the research sector with tools to solve a particular problem. And the hypothesis there is that that will help this rate limiting step in the context of getting a CDR industry off the ground. So we're judicious in our target. Yeah.
Sure. Great, thanks. I'm not seeing any. Oh, there's one question. Okay, we can take a question from online. Daniel asks, what activities have been undertaken to understand and address the potential influence of implementing various ocean MCDR techniques on the broader ecosystems? CDRs
And then this is from Joe. Okay, so the answer to that question. So what activities? Okay, so there's been a lot of activities associated with ecosystem impacts. Most of the studies, for example, that have been done on ocean alkalinity enhancement show that it has relatively low, presents relatively low risk for large-scale ecosystem impacts. The types of studies that have been done are ecotoxicological studies, where you look at sort of lethal thresholds, and sort of physiological studies looking at algal growth rates or impacts on zooplankton. Those are sort of the lower trophic levels of marine ecosystems, and those studies have been done in laboratory and mesocosm settings. I think one key point in that space is that the ocean is enormous. I mean, we've gone through calculations, right, about how much alkalinity we need to put in the context of a field trial to discern a detectable signal in the environment. And the paradigm that arises in that space is sort of mixing zone theory, that is a coastal engineering, wastewater engineering, paradigm. Ocean alkalinity enhancement signals from point sources are basically indistinguishable. The signal associated with those are indistinguishable after a few hundred meters, right, for any sizable release. And so, almost by definition, the likelihood, of having there's a potential for near field impacts to generate ecosystem, or sort of near field concentrations to generate ecosystem impacts. But it seems to me quite unlikely that large scale deployment of these abiotic approaches will be very concerning in the ecosystem space. I think that's a bit different for the biotic technique. So ocean iron fertilization is necessarily moving nutrients around in the global overturning circulation. And so there's been studies that show that deploying iron fertilization in the Southern Ocean, for example, has an impact on fisheries, but not for a few decades later, until the subantarctic and Antarctic intermediate water pops up again in the subtropics. Similarly, macroalgae cultivation changes macrofaunal assemblages and can also contribute to nutrient robbing. So it's still a moving. There's a lot of movement in that space, but I think the basic principle is that yes, where signals are strong in the near field, there's the potential for ecosystem impacts. But as you move farther out for these abiotic technologies, the signals are sufficiently diffuse that it's unlikely to cause significant harm.
Next question. Yep. Yeah.
Yeah, so my question is, are there any, with recent field trial with the MCDR approaches, should those results of the field trial be compared with the model estimation for the MCDR, or is the model sufficiently good with the MCDR approach? Yeah.
Yeah, that's a great question. So there are several field trials that are sort of in various stages. There's a significant one this past late summer, fall, conducted by Woods Hole in the Gulf of Maine, where I can't remember, something like 30 tons of sodium hydroxide was released in the surface ocean, and they did a very comprehensive sampling plan and looked at sort of the response in the ocean. And then they're building modeling systems of that system. There's also an installation in Port Angeles, Washington, that's running now. releasing alkalinity. I think there's sort of pulling the system apart. I mean, I think the first order thing is understanding the fidelity of the flow and where plumes go, and then understanding the carbonate system response, and then whether there is any significant feedbacks. And so, we have a pretty good understanding. We have fundamental governing equations for the flow, but of course models have imprecise boundary conditions and need to be evaluated in that space. Carbonate system chemistry, again, we have a very good handle on the theory, but there is some wiggle room. And then feedbacks are obviously, have some, for example, you might change sediment water exchange. So it's an ongoing area. People are starting to conduct field trials and have an opportunity to assess models against those data.
Okay, let's do 2 more questions. We'll start with Carrie Chow online. Is the ocean CDR market and funding hugely affected by international climate negotiation progress?
I don't know.
Okay. That's great. David.
Yeah, thanks for a great talk. You focused mostly on global benefits in your talk. I wonder if you also think about regional benefits, and are there, could the tools you're building be used to make a case for benefits in specific regions that might get community interest instead of just the purely global?
Yeah, totally. So I think there's two primary axes there. One is the impact on livelihoods, and there's been some, there's a report by the Rhodium Group, for example, that quantifies the projected job creation in the US for deployment of durable CDR technology. So there's some modest advantages there. The second thing is related to mitigation of things like ocean acidification. And actually there's really interesting developments now in the Pacific Northwest where there's a lot of awareness of ocean acidification. Actually, large indigenous populations that are very interested in ocean alkalinity enhancement, not so much for carbon removal, but for ocean acidification mitigation. Okay.
All right, one last question. Look in this side of the room. Enrico.
I have a question about the sequestration, the subsurface sequestration of the CO2 from the ocean. Like that technology, I find it in general quite complex to already with extracting the CO2 from the air. Isn't this adding another layer of complexity in the whole chain of the technology? Like why is that used, explored, compared to directly extracting from the atmosphere?
Yeah, okay, so there is another complexity. So extracting carbon from seawater introduces the requirement for that parcel of water to re-equilibrate with the atmosphere. I think that's your question, is that?
Yeah, like there is an extra step.
Right, so, I think it's just a question of cost. And, there are companies who think that they can build cost-effective direct ocean capture facilities. The analysis that we've done shows some dependency on how much you care about re-equilibration. I mean, you care about re-equilibration, but it's likely to be the case that for over most of the sort of low latitude ocean, you re-equilibrate on a timescale of about a decade or 2. Now, if you care about the year-to-year trajectory, then you have to get more detailed and more refined. Direct air capture is costly, and so it's just sort of these competing technologies where companies are exploring that space. The same is true for ocean alkalinity enhancement or macroalgae cultivation. You need to have that re-equilibration step, and so that's just sort of baked in to the problem. I think leveraging the ocean as this massive compactor is really what the appeal is.
Okay, thanks everyone for the great questions. Before we conclude, I want to remind the participants of the Crocodile Workshop that we will have a photo in front of the building immediately after the seminar. So let's thank Matt one more time.